So what I'm going to do to be able to estimate the solutions to this equation, y, or 2 to the x is equal to 10, is I'm going to go to my y equals window, and in y1 I'm going to enter the exponential function 2 to the x power. In y2 I'm going to enter y equals 10, which will give me a horizontal line at positive 10. Now a standard viewing window would possibly work here, except that what I'll find is that line y equals 10 will be at the very top of the screen and therefore a bit difficult to see. So what I did then was I went to Window and I changed my y max to 15, just so I could go a little bit higher than 10 so that I could more clearly see this line at y equals 10. So I hit Graph. When I hit Graph, you should see the window that's displayed here. Now I see my exponential function, which is intersecting the y-axis here at positive 1. And the reason it's intersecting at positive 1 is because this number out in front of the power, the starting amount, the a value, is actually equal to positive 1. And that's always equal to the y-intercept. What I'm looking for is this place where the exponential function y equals 2 to the x power intersects the horizontal line at y equals 10. So to find that exact location, what I've done here is I've hit second, trace, and I'm sure you did this in Algebra 1 last year, intersect, which is option 5, and then I hit enter for the first curve, enter for the second curve, and enter to guess. And when I do that, it tells me that the x value on that exponential function, where y is equal to 10, is equal to about 3.322. Now, exponential functions have some unique properties. First of all, they always are functions that either look like this, which represents exponential growth, because as you move left to right on the graph, it's going in an upward direction, or they look like this, which represents exponential decay, because as x is increasing, y is decreasing. All exponential functions, whether they're growth or decay, have a domain that's equal to all real numbers. The reason for this is because if you look at both of these graphs and move from left to right, they continue on into infinity. So the domain never stops. It's all real numbers. Range is always about how high and low the graph goes. Well, you'll notice, though, that these exponential functions, whether they're growth or decay, only increase above 0. They never actually get to 0. And therefore, their range is all real numbers greater than 0, or you could say all positive real numbers. As I mentioned, in an exponential function in the form y equals a times b to the x, a is always the starting amount. So a will always be the y-intercept. And finally, because you continually multiply by a number other than 0, you'll find that exponential growth and exponential decay functions never ever get to 0. So the graph of both of them, decay and growth, never intersect the x-axis. Now, as we said previously, when it's growth, you have to multiply by a number bigger than 1. And that's why the b value, which is the base of the power, has to be a number bigger than 1 to make it grow. We say with exponential growth that it is strictly increasing, That means it just keeps going and going and going in an upward direction without any boundaries of any kind. Although, as x decreases, so if you picture this, as x is getting smaller, so as you move left on the coordinate plane, what you find is that the curve is decreasing and is approaching 0, but never ever gets there. And you learned in Algebra 1 last year that when a graph approaches a particular line but can never get to that line is called an asymptote. With exponential decay, as we mentioned previously, the base, b, to make something smaller, you have to multiply by a number less than 1. And therefore, the base b has to be a number less than 1. Therefore, we say, with exponential decay, that function is strictly decreasing. So, as x moves, as x increases, so as you move right on that graph, you see that the exponential function continues to decrease and decrease and decrease and decrease. It decreases as x decreases, the function y, or f of x, gets bigger. So let me show you what I'm talking about. As x decreases, so as you move left on this graph, you notice that that curvature is moving in an upward direction. Therefore, it increases without boundary. On the other hand, as x increases, so as you move in a direction to the right, you notice that that curve is getting smaller and smaller and smaller. So f of x, or y, decreases. And it gets closer and closer to 0, but never ever gets there.